Okay, I want you to close your eyes for a second. Picture a small, idyllic town. Let's call it Smallville.
Okay. Smallville. Got it.
You drop 25 people into this town. They wake up in their beds. They brush their teeth. They make breakfast. You know, the usual.
Right.
Some of them are artists. Some are writers. Some work at the local pharmacy. They head out the door. They gossip at the water cooler. They form opinions about each other.
Sounds like a standard small town life. A little sleepy, maybe a little drama.
It is. Until one of them, let's call her Isabella, decides on a whim that she wants to throw a Valentine's Day party.
Uh-huh.
Now, here is the kicker. Nobody told her to do this. There was no script. There was no human hitting a button that said, initiate party sequence.
So she just decided.
She just decided. She checked her calendar, she realized the date, and she started inviting people.
And the other people actually showed up. I mean, did it work?
They did. They checked their own schedules. They coordinated dates with their crushes. And yes, they had crushes. And they all showed up at the right place, the right time.
Okay, so for anyone who hasn't seen the headlines, we aren't talking about a reality TV show here.
No.
We're talking about generative agents.
Exactly. The paper from Stanford and Google, and it's arguably one of the most important experiments in recent AI history. Because these weren't humans.
No.
There were 25 instances of ChatGPT essentially running in a sandbox, just living autonomously.
It's like The Sims, but with actual brains.
Right.
Which, that really is the hook for today's deep dive, isn't it? We aren't just talking about chatbots anymore.
Not at all. We are doing a deep dive into the evolution of AI agents. We're going to answer a really specific question. How did we get from a chatbot that just predicts the next word to a digital entity that can plan a party, conduct chemical research, or even write code to fix its own errors?
And looking at the stack of papers you've brought today, this isn't just a story about models got bigger, is it? I feel like that's the common narrative, just add more chips, get more smarts.
No, not at all. In fact, some of the most important breakthroughs, and we'll get into this, came from making models smaller but smarter. We're going to trace the timeline from the Big Bang in 2017 all the way to the self-evolving agent societies of today.
Okay.
It is a specific sequence of technical breakthroughs. Think of that like a layer cake of cognition that got us here.
I love a good layer cake. But, usually the bottom layer is the most dense. Where does our story technically start?
It starts in 2017 with a paper that has perhaps the most confident title in computer science history. Attention is all you need.
Ashish Vaswani and the Google team. The birth of the transformer.
The birth of the transformer. Now, to understand why this was the Big Bang, we have to look at the dark ages before 2017. Before the transformer, if you wanted an AI to, say, translate a sentence from English to German, you generally used recurrent neural networks, or RNNs.
Right, and the problem with RNNs, if I recall correctly, was that they read like a human with tunnel vision.
That's a perfect way to put it. They process data sequentially. Word 1, then word 2, then word 3. If you had a long paragraph, by the time the model got to the end, it had often forgotten the context of the beginning.
That's the vanishing gradient problem, right?
Yeah, exactly. It's like trying to understand a massive painting, like the Mona Lisa, but you can only look at it through a paper towel tube, inch by inch. You have no peripheral vision.
And because it was sequential, it was just slow. You couldn't parallelize it. You couldn't throw 1,000 GPUs at it because step B had to wait for step A to finish.
Precisely. The transformer changed the physics of the problem.
Yeah.
It introduced self-attention. Instead of reading sequentially, the transformer looks at the entire sentence at once.
The whole thing.
The whole thing. It weighs the relationship of every word to every other word simultaneously.
So it sees that the word bank in the beginning of a sentence relates to the word river at the end. And it knows that instantly, rather than waiting to get there.
Right. It creates this massive map of relationships all at once. And because of that, you can parallelize the training. This is what allowed us to start training on the entire internet. It was a complete paradigm shift.
So what was the proof? What did the paper actually show?
Well, the paper showed it immediately. They achieved a BLEU score of 28.4 on English to German translation.
Which, to be fair, sounds like just a random number to a layperson. Why does 28.4 matter?
In the context of the time, it was huge. It beat the best ensemble models, which are usually these heavy, clunky combinations of multiple systems, at a fraction of the computational cost. This became the computational substrate.
The foundation.
The foundation. Every major model you hear about today, GPT, Claude, Llama, they're all transformers. They all run on this engine.
Okay, so we have the engine. But an engine isn't a car. We still needed to figure out how to drive it.
Which brings us to section 1 of our timeline. The rise of GPT, generative pre-training. This is where OpenAI enters the chat around 2018. The insight from Alec Radford and his team was, well, it was relatively simple but radical.
What was it?
Stop trying to teach the AI specific tasks with labeled data.
Right, don't give it a data set of, here's a sentence, here's the translation.
Exactly. Instead, just train it to predict the next token. Feed it a massive corpus of textbooks, websites, articles, and force it to guess what comes next over and over and over again. This is unsupervised learning.
And the assumption was, if it gets good enough at predicting the next word, it must implicitly understand the structure of language, of logic, of everything.
And that assumption paid off in a way that, frankly, scared people. When they released GPT-2 in 2019, they saw emergence.
Emergence, that's a key word here.
It is. They scaled the model to 1.5 billion parameters, which felt huge at the time. And suddenly, without being explicitly taught, the model could translate French to English. It could answer trivia questions. It could write halfway decent poetry.
It was a zero-shot learner. It could do things it hadn't seen in the training data specifically labeled as a task.
Exactly. It was a generalist. But the real earthquake happened in 2020 with GPT-3. The paper was Language Models Are Few-Shot Learners.
This is the 175 billion parameter monster.
175 billion. A massive, massive jump in scale. But the key insight here wasn't just size. It was in-context learning. This is the moment prompting, as we know it was born.
What do you mean by that?
The researchers realized you didn't need to change the neural network's weights to teach it a new trick. You just had to provide examples in the input window.
So you say, here is a math problem, here is the answer, here is another one, here is the answer, now solve this one. You're just showing it, not training it.
And it worked. It learned from the context. But, and this is a huge but, for our story about Agents GPT-3 had a fatal flaw.
I remember playing with early GPT-3. It was eccentric, a little unhinged. Was it a brilliant sociopath?
It was an unaligned text completion engine. It wasn't insistent. If you asked GPT-3, how do I make a cake? It might reply with, and how do I make a pie? Because it thought it was completing a list of questions it found on some internet forum.
It didn't understand intent. It just understood probability. It was just pattern matching.
Exactly. It was smart, but it wasn't helpful. It was a simulator, not an agent. To turn this raw intelligence into something that could actually follow orders, we needed the next layer of the cake.
Okay.
This brings us to Section 2. Taming the model.
This is the 2021-2022 era. We're talking about instruction tuning, right?
Right. The two big papers here are FLAN and T0. Let's look at T0 from San and his colleagues in 2022. They did something fascinating. They took a model, and instead of just feeding it raw text, they fed it tasks, phrased as instructions. Summarize this article, translate this sentence, explain this reasoning.
So they explicitly taught it the concept of following orders. It wasn't just about prediction anymore. It was about execution.
And the results were staggering. This is one of my favorite stats in this entire stack because it completely challenges the bigger is better narrative. The T0 model had 11 billion parameters. GPT-3 had 175 billion, so T0 was what, 16 times smaller?
David and Goliath.
And David won.
Yeah.
T0 outperformed GPT-3 on 9 out of 11 benchmark datasets.
Wait, say that again? The model that was 16 times smaller beat the giant.
It did.
That is wild. It implies that how you teach the model is actually more important than how big its brain is.
It destroys the myth that parameter count is the only metric that matters. But even with instruction tuning, you have a safety problem. The model might follow your instructions, but what if your instructions are bad?
Or what if the model's idea of a good answer is technically correct, but, socially toxic or just unhelpful?
Exactly. Which brings us to RLHF, Reinforcement Learning from Human Feedback.
The big one. This is the Instruct GPT paper by Yu Yang and the OpenAI team. This is the bridge to ChatGPT.
It is the bridge.
I always struggle with RLHF because it sounds like jargon soup. Can you explain it simply?
Think of it like training a dog, but a very, very sophisticated dog.
Okay, I'm with you. A digital golden retriever.
So first you have the dog perform a trick. The model generates an answer. Then a human looks at that answer and several other potential answers and ranks them. This one is good, this one is aggressive, this one is nonsensical.
So the human isn't writing the code, they are just providing the taste. They are the critic.
Precisely. They are the judge. That ranking data is then used to train a separate AI called a reward model. The reward model learns to predict what the human would like. It becomes the person holding the treat.
And then you let the main model run millions of times, and the reward model gives it a digital treat every time it gets it right, and it optimizes for that treat.
That's the reinforcement learning part, specifically using an algorithm called PPO, Proximal Policy Optimization, and the impact of this was just undeniable. In the paper, human evaluators preferred the output of a 1.3 billion parameter InstructGPT model over the massive 175 billion parameter GPT-3 model.
Okay, by how much?
85% of the time.
85%. That is a landslide. It's not even close.
It made the models truthful, less toxic, and more conversational. It gave them manners.
So by 2022, we have a model that is smart thanks to the transformer. It's learned from the world through GPT, and now it's well-behaved because of RLHF. It's still just a chatbot.
Still just a chatbot.
If I ask it a hard math problem, it still hallucinates. If I ask it to book me a flight, it can't.
Because it doesn't know how to think before it speaks. It's operating on pure intuition, what psychologists call System 1 thinking. Fast, automatic, but prone to error.
Right.
To get an agent, we need System 2. We need deliberation.
This is Section 3, Learning to Think. This feels like a big step.
It is. The breakthrough here seems almost too simple to work. It's called Chain of Thought Prompting. Jason Y. and the team at Google, 2022.
Is this the famous Let's Think Step-by-Step paper?
That's the one. They found that if you simply add that phrase, let's think step by step, to the prompt, or if you provide a few examples of reasoning chains, the model's performance on complex tasks just skyrockets.
Wait, hold on. Why, though? Why does asking it to show its work make it smarter? It's the same model weights. Nothing changed under the hood.
It comes back to the transformer architecture. Remember, the model generates one word at a time based on what came before it. If you force the model to write out the intermediate steps, first I need to subtract 5 from 10, which leaves 5, that reasoning becomes part of the context for the next word it generates.
Oh, I see. So it's literally writing its own scratch pad into memory so it doesn't lose track of the problem?
Exactly. It decomposes the problem for itself in real time. But they didn't stop there. Because sometimes, even if you think step by step, you make a mistake in step 2, and then the whole answer is wrong.
Right. One arithmetic error early on ruins the whole chain, so how do you fix that?
You use self-consistency. This was a paper by Wang and his colleagues. Instead of asking the model for just one chain of thought, you ask it for 10 or 40. You generate multiple reasoning paths, and then you take a majority vote on the final answer.
It's like phone a friend, but the friends are just parallel versions of yourself having different thoughts.
And it works. On the GSMAK math benchmark, self-consistency improved performance by 17.9%. That is a massive jump just by asking the model to double-check its work in a few different ways.
But there's a limit to that, right? I mean, if the problem is really, really complex, just thinking about it in different ways won't help. You need to break it down into smaller pieces first.
That's least to most prompting. Denny Zhu's work. This is absolutely vital for agents. It teaches the model to explicitly break a complex problem into subproblems. It asks, to solve X, what do I need to solve first? And the model answers, first I need to solve Y.
Give me the stats on that. I know you have them in that stack.
Okay, on the SCAN benchmark, which tests compositional generalization, basically handling new combinations of commands, standard chain of thought had an accuracy of about 16%.
16%? That's terrible. That's basically failing.
It is, but least to most prompting, it hit 99.7%.
From 16% to 99.7%. That is the difference between a toy and a tool.
It is the difference between guessing and planning. This enables what's called hierarchical task decomposition. The model is no longer just reacting, it is structuring its own behavior.
Okay, so now we have a thinker, we have a planner. But I keep coming back to this. It's still a brain in a jar.
It's still trapped.
It can't do anything. It can't search Google. It can't save a file. It's stuck inside the text box.
And this is the pivot point. This is the moment everything changes. Section 4, the pivot to agency. The year is late 2022, early 2023. If you only read one paper from this entire stack we're talking about today, read this one, React.
React. Synergizing reasoning and acting in language models. This one felt different when it came out.
It was. Before React, you had two camps. You had the reasoning camp, the chain of thought people, and you had the acting camp with models like WebGPT that could send search queries. But they were separate.
React mashed them together.
It created a loop, a simple, elegant loop, thought, action, observation.
Walk us through that loop. How does it actually look in practice?
Okay, imagine you ask an agent, who is the quarterback for the team that won the Super Bowl in 1998?
Okay.
Step 1, thought. The model thinks to itself, I need to find out who won the Super Bowl in 1998. It forms an internal plan. Step 2, action. Based on that thought, it generates a specific command. Search Super Bowl 1998 winner.
So it's not just text, it's a command for a tool.
Right. And then step 3, observation. The environment, in this case Google, returns the text Denver Broncos.
So it pauses, it waits for the result from the outside world, and then it reads it.
Exactly. Then step 4, thought. Okay, the Broncos won. Now I need to find their quarterback from that year. The plan is updated based on the new information.
And then acts again.
Step 5, action. Search Denver Broncos quarterback 1998, and so on.
It's interleaving the thinking with the doing. It's interacting with the world to get new information, then updating its plan on the fly.
Yes. It's the difference between planning an entire vacation in your head before you even open your laptop versus sitting at the computer checking flight prices, seeing they are too expensive, and pivoting to a train trip. You are reacting to reality.
That's a great analogy. And the performance gain from this loop.
On the ALF World Benchmark, which simulates text-based decision-making like, go put the apple in the fridge, React didn't just win, it dominated. It outperformed imitation learning methods by an absolute success rate of 34%.
34% is not an incremental gain.
It was a step change in capability. It was the birth of the modern agent architecture.
But to do this, the model needs tools. It needs to know how to use that search bar, or a calculator, or a calendar API.
This is the concept of grounding and tool use. And here we have to mention Toolformer by Timo Schick and his team at Meta.
This was the self-taught tool user, right? This one blew my mind.
Yes. Instead of humans painstakingly labeling data saying, use a calculator here, Toolformer taught itself to use tools.
How?
It learned to insert API calls into its own text generation. It basically realized, through trial and error, I am bad at arithmetic. My predictions are more accurate if I call the calculator API here, so I will learn to do that.
That feels incredibly human. I don't know this, let me Google it, or I can't do this math in my head, let me grab a calculator.
It's a hybrid of language and function execution. And of course, we can't ignore ag-retrieval augmented generation.
I like to think of Array as giving the model a library card.
That's the perfect analogy. Instead of relying only on its internal memory, which can be out of date or just plain wrong,
It's weights.
right, it can go and fetch documents from an external database. It solves the hallucination problem, or at least helps a lot, because it can point to the source. It can say, I believe the answer is X, and here's the document that says so.
So let's recap the stack so far. We have the brain, which is the transformer plus GPT. We have the conscience, which is RLHF. We have the logic, which is chain of thought and its variations. And now we have the hands and eyes, which is the React loop plus tools and RAG.
That's the stack. So now we get to the final layer, the society.
Yeah.
What happens when you put these agents together? This brings us all the way back to Isabella and her Valentine's Day party.
Back to the generative agents paper. So that's how they did it, with this whole stack.
This is the stack they built on. But the brilliance of that paper wasn't just the simulation. It was the specific architecture they built to make it happen. They gave each agent a memory stream.
Which is like a diary of everything that ever happened to them.
Everything. I woke up at 8:02 a.m. I saw the fridge is empty. I talked to Klaus about his painting. But you can't feed 1 million diary entries into a context window. It's just too much data.
Right, the model would choke.
So they added a reflection mechanism.
This is key. Explain reflection.
The agent periodically pauses and synthesizes its raw memories into higher-level insights. It looks at a dozen low-level memories like, I saw the fridge is empty, I feel hungry, I have no milk, and it creates a new higher-level memory. I should go buy groceries.
So it turns raw data into wisdom,
Right.
into a plan.
Exactly. And the memory, I enjoy social gatherings, plus I see the calendar says it's February 14th, plus I like Sam, became the reflection that led to the plan for the party. The social behaviors, the coordination, the memory, the relationships, they all emerge naturally from this cycle of memory, reflection, and planning.
But memory is still a bottleneck, isn't it? I mean, LLMs have a physical limit on how much text they can process at once, the context window.
It is, but that's being solved as we speak. There's a paper called MEMGPT from 2024. They treat the LLM like a computer's operating system.
How so?
You have RAM, the context window, which is super fast but small and expensive, and you have disk, an external database, which is huge and cheap. MEMGPT is a clever system for managing the paging of information in and out of that context window.
So an agent could theoretically remember a specific detail from a conversation we had 5 years ago simply by pulling it from its disk storage into its RAM when it becomes relevant.
Precisely. It allows for effectively infinite context, which is a huge deal for long-term agency.
Now, we've talked about agents living in a village, but what about agents working? What about multi-agent collaboration?
This is where things get really efficient, maybe a little strange. There's a framework called CAML and another one called AutoGen for Microsoft. The core idea is inception prompting.
Inception prompting.
You create two agents, an AI user and an AI assistant, and you just let them talk to each other.
With no human in the loop.
No human in the loop. You give them a vague goal, like build me a stock trading bot. The AI assistant proposes a plan. The AI user critiques it. This code is missing error handling. The assistant says, you're right, let me fix that. They loop back and forth until the task is done.
It's pair programming, but with two AIs.
It's autonomous pair programming. And when you combine this with advanced reasoning structures like Tree of Thoughts, the results are just mind-bending.
Tree of Thoughts.
Yeah.
This is the chess engine approach, right? Looking ahead, exploring different moves.
Yes, exactly. Remember the game of 24. It's a math puzzle. You have 4 numbers, and you have to use basic arithmetic to make them equal 24. It requires deep look ahead and creativity.
Okay.
Standard GPT-4, even with chain of thought, failed miserably at this. It solved about 4% of them.
4%. That's basically random guessing.
But with Tree of Thoughts, where the model explores different branches of reasoning, backtracks if it hits a dead end, and actively searches the solution space like a chess program, it solved 74%.
From 4% to 74%. Again, the model didn't get bigger. The process got better.
The cognitive architecture got better. There is one final capability we have to touch on, though. The ability to learn from mistakes. Humans screw up, we realize it, and we try to do better next time. Can agents do that?
This is the reflection paper, spelled with an X.
That's the one. It's a form of verbal reinforcement learning. Usually, to teach a model, you have to do all this complicated backpropagation and update its weights. That's slow and expensive. Reflection doesn't touch the weights at all.
It just writes a note to itself.
Essentially, yes. If it fails a coding task, it analyzes why. It generates a short, natural language reflection. My previous attempt failed because I forgot to import the NumPy library. It stored that reflection in its episodic memory.
I see.
The next time it tries the task, it retrieves that memory as part of its context. Note to self, don't forget to import the library.
It's like keeping a journal of your failures so you don't repeat them. That's incredible.
And the stat on this one. On the Human Evil Coding Benchmark, a standard GPT-4 agent scored about 80%. A reflection agent using that same GPT-4 scored 91%.
Just by being allowed to critique itself and remember its own mistakes.
So, looking at this whole timeline, this whole layer cake we've built, from the transformer to GPT to RLHF to chain of thought to React to memory to self-correction, what's the big thing that stands out to you?
Honestly, it's the modularity, the compositional nature of it all. We keep waiting for one giant God model that does everything, but that's not what's happening.
No.
The reality is that we are building a system. The LLM is just the CPU, but to get a true agent, you need the RAM, which is the memory stream. You need the disk, which is RGE. You need the controller and the I/O, which is the React loop. It's an architecture.
We are entering the era of cognitive architectures. We aren't just prompting models anymore. We are engineering flowcharts of thought.
And we are seeing this bear fruit in the real world with things like Agent Hospital and CoScientist.
Right. Agent Hospital is a simulation where medical agents actually evolved their practice. They treated simulated patients, they learned from the outcomes, and they got better at diagnosis without any humans updating their code.
And CoScientist is doing actual chemistry, planning reactions, writing the code to control robotic lab hardware, and then analyzing the results.
It's a brave new world.
So let me ask the uncomfortable question. If agents can plan, use tools, remember, and fix their own mistakes, what is left for us?
That is the question of the decade, isn't it? But I'll leave you with this thought. The bottleneck, I think, is no longer the AI's capability. We have the stack. The components are there.
So what's the bottleneck?
It's us, is how we design the task we give them. If you treat an agent like a glorified chatbot, you get a chatbot. If you treat it like a cognitive system, give it a high-level goal and the right tools, you get a CoScientist. We need to learn to delegate, not just prompt.
We need to become better managers of Silicon employees.
Exactly. And if you want to see what that management process looks like visually, go look up the diagrams in the Tree of Thoughts paper. It really visualizes how these machines are starting to deliberate. It isn't a straight line anymore.
No.
It's a branching path.
And that path is leading somewhere very, very interesting.
Indeed it is. Thanks for diving in with us.
See you next time.